Black 1, the accidental alien signal. Hello and welcome to a story that combines the thrill of alien contact, the wonder of cosmic discovery, and a controversial moment in scientific history. Imagine it's 1967. The world is a whirlwind of change. The summer of love is in full swing, music is being revolutionized, and humanity is just 2 years away from landing on the moon. But far from the vibrant cultural centers, in the quiet, damp fields of Cambridge, England, a different kind of revolution is brewing. Here, a young, determined postgraduate student named Jocelyn Bell Burnell is about to stumble upon something that would forever alter our map of the universe. Her job was anything but glamorous. She was part of a team that had just built a massive new radio telescope, the Interplanetary Scintillation Array, or IPS array for short. Spanning over 4.5 acres, it was a forest of 2,048 antennas designed to study the twinkling or scintillation of distant radio sources called quasars. Bell Burnell's specific task was to operate this colossal instrument and, most importantly, to analyze its output. And what was that output? Not a sleek digital screen, but reams and reams of paper charts. Every day, nearly 100 feet of paper spooled out of the recorder, covered in squiggly lines representing radio signals from the cosmos. Her job was to scan all of it by eye, looking for the telltale flicker of quasars. It was tedious, painstaking work, requiring immense focus and an almost superhuman ability to spot anomalies in a sea of cosmic static. For months, the routine was the same: scan, analyze, categorize. But then in August 1967, she saw it. A tiny, peculiar smudge on the chart, a bit of scruff that didn't look like a quasar, nor did it look like the usual random interference from earthly sources like car ignitions or faulty equipment. It was something else. Intrigued, she noted its position in the sky. When the telescope scanned that same patch of sky a month later, the scruff was back. This was no random blip. This was a signal, a repeating pattern. When she analyzed it with a higher speed recorder, the true nature of the signal became breathtakingly clear. It wasn't just a pattern, it was a pulse, a perfectly regular repeating radio pulse, arriving every 1.3373 seconds. The precision was staggering, more accurate than any clock on Earth at the time. What could possibly produce such a signal? Natural cosmic objects are typically messy and chaotic. Stars flare, gas clouds churn, galaxies collide. Nothing in the known universe was supposed to behave with this kind of metronomic regularity. The team, led by her supervisor Anthony Hewish, began a frantic process of elimination. Could it be the telescope itself? A faulty wire? They checked everything. Could it be another satellite in a weird orbit? They calculated the timing and ruled it out. The signal kept coming, day after day, locked not to Earth's time, but to sidereal time, the time of the stars. This meant it was definitively coming from deep space. The implications were mind-boggling, and in the privacy of their lab, a tantalizing, half-joking hypothesis was floated. The signal was so artificial, so seemingly intelligent in its regularity, that they nicknamed it LGM-1. The LGM stood for Little Green Men. For a brief, thrilling period, a small group of scientists in Cambridge had to seriously entertain the possibility that they had just discovered a beacon from an extraterrestrial civilization. Can you imagine the weight of that secret, knowing you might be the first person in history to make contact? The scientific community held its breath, but the true nature of this signal, once uncovered, would prove to be even more astounding, and in many ways far more important for our understanding of the universe. It wasn't aliens, it was the birth of a new field of astrophysics. Block 2. The Cosmic Lighthouse and the Nobel Snub. The Little Green Men theory was exhilarating, but science demands rigor, not just romance. As Jocelyn Bell Burnell continued her patient scanning of the sky, the mystery deepened. Just before Christmas, she found a second signal, then a third, and a fourth, all pulsing with their own unique clockwork precision, but all coming from different parts of the sky. The odds of 4 separate alien civilizations all deciding to signal Earth at the same time with the same technology were astronomically low. The LGM hypothesis was dead. The real explanation had to be a new class of natural object, something no one had ever theorized or seen before. The team had discovered the first ever pulsar. But what exactly is a pulsar? To understand it, you have to imagine one of the most extreme objects in the universe, a neutron star. Picture a star much more massive than our sun reaching the end of its life. It explodes in a cataclysmic event called a supernova. While the outer layers are blasted into space, the star's core collapses under its own immense gravity. Protons and electrons are crushed together to form neutrons, creating an object of unimaginable density. Imagine the entire mass of our sun squeezed into a sphere just 12 miles across, a city-sized ball weighing more than a quadrillion tons. A single teaspoon of this material would weigh as much as Mount Everest. Now add another piece to this puzzle: the conservation of angular momentum. Think of a figure skater spinning. When she pulls her arms in, she spins dramatically faster. The same thing happens to the collapsing star. As its mass gets packed into a tiny volume, its rotational speed increases to insane levels. The resulting spinning neutron star can rotate hundreds of times per second. This spinning, hyperdense star also has an incredibly powerful magnetic field which shoots out beams of radio waves from its poles. And here is the key: the magnetic poles are not aligned with the star's rotational axis. So, as the star spins, these beams of energy sweep across the cosmos like the beam of a lighthouse. If Earth happens to be in the path of one of those beams, our radio telescopes will detect a pulse of energy every time the beam sweeps past us. This is what Bell Burnell had found. Not an alien message, but the rhythmic sweep of a cosmic lighthouse, a remnant of a long-dead star. This discovery was a monumental achievement. It confirmed the existence of neutron stars, provided a new tool to probe the interstellar medium, and opened a new window into the physics of extreme environments. The discovery was so significant that in 1974, it was awarded the most prestigious prize in science, the Nobel Prize in Physics. The prize was awarded for the decisive role in the discovery of pulsars. But the recipients were Anthony Hewish, Bell Burnell's supervisor, and Martin Ryle, another senior astronomer at the observatory. Jocelyn Bell Burnell, the graduate student who had spent months poring over the data, who first identified the anomaly, who fought against initial skepticism to prove it was real, and who found the first 4 pulsars, was not included. The decision ignited a firestorm of controversy that continues to this day. Hewish argued that as the head of the project who designed the experiment, the ultimate credit was his. Many others, including prominent astronomer Fred Hoyle, vehemently disagreed, arguing it was a scandalous snub. Bell Burnell handled the situation with incredible grace, stating that it was the norm at the time for senior scientists to get the credit for work done by their students. But the question lingers and has forced a reckoning within the scientific community about how credit is assigned. It is a story not just of a cosmic discovery, but of a human debate about recognition, bias, and the very nature of what it means to discover something. It forces us to ask who truly deserves the credit in science: the one who builds the instrument, or the one who sees the universe through it in a way no one else has before? What do you think? Was the Nobel Committee's decision an unfortunate reflection of the times, or a genuine injustice that should be corrected? Subscribe for more, and see you soon.